Hi guys, welcome to Heat Geek. Today we're at Caldera Heat Battery Storage to find out what it's all about. Let's check it out. Hi guys, Adam from Heat Geek here. I'm at Caldera, which we'll tell you about in a minute, joined by the CEO, James McNaughton. Hello, James.
Hello, Adam.
Thank you for having me here. I was here about 2 years ago. You invited me down to have a look at what you were doing, something a bit interesting in the heating space in domestic. And it was very interesting. You were still developing what was there. However, I've returned today and it's a bit different.
Hi guys, producer Harrison here. For anyone who doesn't know what Caldera do, they build heat batteries with a novel and unique technique. Their system turns renewable energy into zero carbon heat on demand by storing the heat for long periods in recycled aluminium and volcanic rock, which is heated up using an immersion element. They call these heat cells. Caldera originally made these devices for the domestic heating market, but with so much demand from industry for renewable heat, they've recently changed directions. Stick around to find out exactly how these things work and how they could be changing the way big industry generates heat for a variety of different industrial applications.
What do I need to know before we go down?
So when we built our first smaller units, the domestic ones, we put the warm stem material, we put it actually in the center of a vacuum vessel, and we built the vessel around them. So it was like a double skin bottle, and you couldn't get in or take anything out once it was in there because it was all cast in place and welded in place.
Right.
The big change we made was that we went from a vacuum, effectively a vacuum like vessel, to what we call a vacuum tea cozy. And it's a bit like your vacuum coffee mug, which is we turned it upside down and we dropped it over. And this means we can get in and out of the units. Now, when we go downstairs, we're going to see some of the, let's say, the intermediate size units, but it's just nice because we've got a nice little 3D model, and I can show, when you look at them from the outside, you'd like to know what's inside. So first of all, it's double skinned. If you feel it here, it's got 2 walls.
Okay, yeah, for
There's the vacuum tea cozy.
Yeah, so that's 0 atmospheres or something in there, is it?
Exactly, 0 atmospheres inside, fabulous insulation, very compact, and actually we think it's the cheapest solution for doing high temperatures.
And you, that's 3D printed, so this is the same material, is it?
No, so it's all steel that we use.
Right.
And then now this is the big difference. So originally we would have one big block of material cast inside the vessel, and then we'd close it up, and you just have a little entrance point.
Yeah.
Now we have trays, and we're moving to wedges, which you'll also see downstairs. But in the intermediate size, we have 6 trays, all with the material in, and we connect all of the trays up together, so it's like having 6 individual units all plumbed in. And the units downstairs that we weigh about, these are roughly 3/4 of a ton each, so it's 4.5 tons in here. The original unit we had would be 1.5 tons.
Right.
So this is 3 times as much material. Where we're going to is a lot bigger, so you'll start to see.
Yes.
But this is just so that when we go down there and have a look, and I point to your nice shiny steel cylinder, you'll know inside there are all of these trays.
Yes, got it, okay.
Should we go and have a look around the factory?
Yeah, give me a tour, please, thank you.
This was our domestic unit.
Yes, this is the one I remember and I came down and saw.
1.8 tons.
Yeah.
Just looking inside, it's at 464. And as you remember, kilowatt.
Yeah. Slightly above room temperatures, probably like, I don't know, 28, 30 degrees or something on that surface.
So we keep this unit. This still heats the office. So this heats the offices. So we use it. It's just nice to have it here to show people.
That does all of the office space
All of the office space, upstairs, downstairs, all through winter.
Oh, wow, okay. That's probably like a domestic, so I guess there's about 100 metres squared, maybe 120 metres squared of office space. But probably a bit more than that, actually.
We've got one at my house, one at Guy's house, and we have 2 heating a church.
Oh,
so
amazing.
we brought all the other ones back, and actually you'll see some of them outside, but they are basically going for the scrap heap in the sky very shortly. This is a test rig of our intermediate size unit. So these weigh, as I said, it's about 4.5 tons, 3 times the weight of the original ones. And because the cover's on, I wanted to show you what was inside.
Yeah.
So you've got 6 stacks in there, and we've got 10 of these outside.
Right.
all plumbed in, which we're going to go and have a look at probably in a second. But
So what would this be recommended for, this size unit? What kind of, how do you size them? Or
we were sizing this for industrial. We were sizing, so the 10 units outside give us 2 megawatt hours of steam production for a factory. They weigh, with the domestic, because most homes want heat at 50, 60 degrees, we can get a bigger temperature range out of the storage material. So for us, the storage material always never goes above 500. When you're making steam, we only go down to about 250. So there's a shorter range. When we're doing just hot water at 50 degrees, we can drop down to about 150.
Of course.
So we get a bigger range. So this is 3 times as big from a weight perspective, but it's only twice as much energy when we're generating steam. So this is 200 kilowatt hours, and we've got 10 of them outside.
Got you.
So where we're going, the reason this is actually effectively now obsolete already, because we're going to this is 1.2 meter in diameter. We're going to something that's 3 meters in diameter, 7.5 meters high, and it'll have 36 1.5 ton blocks in it.
Wow! Oh my God! So you completely,
so
you really get miles away from that original.
We are going miles away. And what opened it up is once we could make the vacuum tea cozy, and we could split the units down into blocks that you can transport. So originally we were always limited by what you could handle, what you could manage. Now this sort of takes us away from it. We're effectively like Lego, so we can just plug in multiple blocks under one cover. It's really easy to, and by going bigger, it halved the cost.
Right.
So it literally made the most enormous difference to the cost of the system.
You can in theory stack these together as well if you to get.
We can go tall. Yeah, so we can go exactly. So it's sort of 4 megawatt hours is going to be our starting size.
Yeah.
But we want to go twice as high as well. So maybe up to 8 megawatt hours. 12.5 meters tall.
Yeah.
And then if you want multiple, you'll be able to build multiple units.
Got it.
And probably we'll jump outside before running back and going through the factory. You can see some of the smaller domestic ones. So what we did here.
Oh wow. This wasn't here at all?
No, there was a little pad here. There was virtually nothing at all. We've a much bigger pad. Everything's gone in.
Seems really impressive to look at, especially as it's shiny and new.
Yes.
These are the ones that are going back to scrap.
Yeah, so we set up, so to get the system, so we've got a steam network here and we've got a hot water network. And there's a big tank inside we'll walk past that stores 15,000 litres of water. Okay. And we can heat that up from 20 to 90 in about an hour.
Right, wow.
Just a little bit over an hour.
So do you use the steam on site as well?
No, we use it for demonstration. So when I have a customer come here, what I want to be able to say to them is, this steam net looks just the same as yours. Tank is like the sort of thing you'll find in a brewery.
With you.
You can see this is everything that will be on your site, so you can feel very comfortable. And we'll run it for you. And we can run it at full capacity. We put a new transformer in.
Yeah.
So we now have a megawatt supply to the building.
Yeah.
So there's 1,000 kilowatts in there.
Did that involve a new? Right, and that's what this is, I'm guessing.
No, you can see the cable.
Oh yeah.
So we brought the cable in from the.
What was the cable like?
No, so at 11,000 volts, it's tiny. It's
of course, it's 11,000 volts. Yeah.
Now the cables from the transformer into the switchboard and back, they're all nice. Lots of big fat cables. Yeah. And then this brings 500 kilowatts out to the system. Now as we walk through here, you'll see 10 of these units. So there's 2 megawatt hours here. We've got all the electrics, all the steam piping, and we can charge from this box, which has all the electric controls in. And you can see the power coming out of the building.
Yes.
So the aim is for the new unit is the equivalent of 20 of these inside a single cover.
Yeah. Wow, okay.
And it'll be pretty much 3 meters in diameter. So just
3 meters in diameter and height was
7.5, 8 meters. So the building height is 9 meters, so it'll be just underneath the top of the building.
Okay, that would be impressive to look at, yeah. Amazing. What's going on over there?
If you remember, so within our system, we always take the heat out as steam. So we have a little loop, we have a coil inside each block. And actually, this is great because you're going to be doing this later. Okay. So we're going to do a little steam generation. So what we do is, because the blocks change, they go up and down in temperature. We want a very simple way of taking the heat out. So we put a steel coil inside each block, and when we want to extract heat, we squirt a bit of water in, and we flash it completely to steam.
Yeah.
So it's a bit like I always say. So basically, the more water I put in, the more steam I generate, the more heat I take out, and then we control the amount of water we put in from nothing. So if I put nothing in, it just sits there and happy. If I want to take heat out, turn it, I can turn it up. So it's like a tap.
Heat tap.
But we want really pure water in our circuit. So we put in sort of distilled water, and then by the time it's been distilled, you know, tens of thousands of times, it's just a small amount of water runs around the circuit. We don't want water from outside going into the system.
You don't want
we
the
need a heat
impurities.
exchanger.
Right.
So we did the same for the home units as well. So we have our bit, which is just clean, has a little bit of water and a pump, and then we put a heat exchanger in. This is a steam generator.
Okay.
So this big unit over here
Yeah.
takes the steam out of our circuit, and it then boils water, which is on what would be the customer side, and it generates steam, which comes out, and it goes into this network, and the steam flows around, and it goes into the factory to heat the hot water cylinder, and there's a jacket around the hot water cylinder.
Yeah, got it.
And the reason people use steam in industry, 2 reasons. Actually, there are probably 3 reasons. First of all, it pumps itself. So once you pump the water up and it boils, it just always runs to the lowest pressure point. Second reason is very easy to control the temperature.
Yes.
If you're, for example, boiling something or cooking something and you don't want to burn it, if you set the steam pressure just right, then you know exactly when all the heat is transferred. When it goes from steam back to water, it gives off the most enormous amount of heat.
Yes.
And then the third reason is that it's also the cheapest way of moving heat around. So steam, because of the energy change from when you go from a liquid to a gas and back again, it actually means the pipes are much smaller than if you even did it with hot water. So you find in a lot of factories, hospitals, industries, they just use heat. They have these big boiler houses with these great big boilers burning away gas 24 hours a day, and they generate steam and they pump it all around the site in these big pipes. These are relatively small. You know, this is like for a ton an hour of steam. You might have 10, 20 tons an hour, you know, more. So this is why people use steam, and we're focused on it because it's actually quite hard to decarbonize with heat pumps. Which you will also know.
And your hospitals makes a lot of sense. Like you're taking heat directly to point of use. You haven't got those Legionella kind of issues, and you could just literally turn it off when you don't need it, so you don't emit the heat. Plus the smaller pipe work, etc. All makes a lot of sense. And is the return liner bigger? The water
return line's much smaller because it's a condensate line, so it's only the actual liquid.
With you. And it's only used, typically you don't use the gravity effect to circulate, or is
no, it tends to come back. So normally if you sort of take it, so if let's say a circuit will be running at, I'm going to use numbers 10 bar because it's easy. 10 bar is 183 degrees. It turns from steam back to water. Right. But as long as you have, when the water goes back to the boiler house, they tend to drop the pressure at that point. Right. If there are some reasons they do that. So effectively you do have the pressure in the network that tends to bring the condensate back. The bigger problem is often with these steam pipes, which is that there's a little bit of cooling and you do tend to get liquid forming, and every now and then you have to manage the droplets because you don't want steam and water in the same pipe.
That's in installation as well, right? So,
so they angle things down, and then at the lowest point you have a little something called a steam trap, which takes the water out and returns it to the condensate.
Amazing. I'm just going to ask you about this heat exchanger quickly. The bottom part was the heat exchanger, or the
bottom part is so the bottom part has got some pipes in from our side.
But the steam generator is essentially a heat exchanger.
It's a heat exchanger, yes.
Right. Would this be? Is that like a shell, tube in shell?
Yes. Shell and tube. Exactly.
Like so have you seen the mini store we've created? It's like a solution for hot water.
I know you have done a little store that goes in a cupboard.
I didn't know the term shell in tube. It turns out people call it thermal store, which is incorrect. It's a shell in tube heat exchanger, and that's a big daddy version of
that is
the
a
mini
big
store.
daddy version.
Okay.
And we're also, so that's a big daddy version. Again, because this was the first off, there were certain things we put on there that we thought we didn't need, but we now can take off, so we can shrink it down. And so the aim is you'll have a much smaller version of this next to one big.
Yes. Got it. That makes a lot of sense.
Here, this is what happens when you run a steam network. So you need to process the water. You need to make sure. So if you imagine you need to make sure you don't get corrosion. So there are certain chemicals you add to the process. So this is all the traditional equipment that you would have for a steam network. And then on this side, the second way we have of heating is we can take steam to a plate heat exchanger, and we can just heat water. So if you imagine the original home units, this is just a big version of what we do in the home units. So
plate heat exchanger there, I see.
Yeah. So plate heat exchanger here, steam comes in one side from our side. It's all nice and clean. It comes out as water, and we pump the other side. We pump water through from the tank. So we've got 2 ways of heating the tank. One is just to take water out, run it through here. It comes back at 90.
Yeah.
The other way is to take steam and put it around the outside of the big tank,
Yeah.
and that's the second way. So we
Yeah,
can do it either way, and we wanted just to demonstrate this.
Yes,
So
yes.
this is what happens when you go industrial. Everyone gets a little bit bigger.
Yeah, amazing. A couple of quick questions, and we'll probably cover this elsewhere as well. When you generate steam, obviously water expands 1,600 times. How is that managed? We're keeping that in the system, and it just gets higher pressure. Is that right?
So the pressure. Right. So when you boil the water, probably the easy way to run it is there will be a balance point. So if you say I want to run my steam network at, let's say, 10 bar. When people start to take steam off and cool it, the pressure drops.
Yes.
So what everyone does is you measure the pressure at, say, the steam header, which is by the boilers, and you go, I want it to be 10 bar. Yeah. If it rises above 10 bar, I turn the boilers down. Right. And if it drops, I turn them up. And therefore, by measuring as long as the pressure's at 10, yes, I'm matching supply and demand. It's a bit like the frequency on a grid. So you turn it up. So we do the same thing, and you normally have different boilers. So if it drops below 6, then the standby boiler kicks in, because clearly there's a lot of heat being used. Got it. And likewise, you can just turn them right off if there's no demand at all.
That's just that tap, with the heat tap that we were talking about.
For us, it's just the water circuit. For a normal boiler, it'd be gas, so they turn gas up and down.
Okay, and that's the water that goes into the shell and tube heat exchanger.
Yes, that's correct. So the water in our circuit, there's only a little tank in our circuit. So I'm just trying to think where the one is here. Just around that side. We only have a relatively small amount of water in our circuit, which makes it really safe. Right. So most of the water there is on the customer side, and if you had a traditional gas boiler, you have to make sure it never drops below a certain level, because then the tubes can get too hot.
Yes.
So whereas what we have is we have hardly any water in our system. It's almost completely dry. All the energy is stored in the aluminium and rock. So when it goes through, so much better for unmanned operation, and just fundamentally safer because we can't actually overheat the system.
Yes, of course. And then and the water storage that's kept for that's in.
The water storage is only about 20 litres. It's
only 20 litres.
Whereas inside the tank we'll have a few tons.
And that's basically almost never replaced.
Should never be. Our side should never be replaced.
So it's filled with some kind of Demming thing on site.
It doesn't matter, because once it's been distilled, because
it
gets distilled so many times.
It's cleaned immediately,
which is why we just want the same water going around and around.
Right, of course.
Then there's nothing in there.
So actually, you could just fill it tap water, probably.
You probably could, but
not best practice.
Not best practice.
With you. Cool. I mean, already I'm a bit blown away, because I was only here 2 years ago and none of that was happening. So that's incredible.
Just a little this.
Yeah.
This is some tooling. We're going to go and look at some wedges in a second.
Okay.
So, do you remember Trivial Pursuit?
Yes. The wedges in Trivial Pursuit. Yeah.
We've gone to Trivial Pursuit wedges now.
Okay, so. That sounds fun.
We're going to start with the hot water tank, just to fill up the scale.
Yeah.
So this is a 15,000 litre hot water tank.
Yes.
Sort of thing you'll find in a brewery.
Yes.
And there's two ways. There's an insulation around it, and underneath that there is a little dimple plate jacket, so you can put steam in there and heat the water inside the tank directly, or we can pump water out of the tank through the heat exchanger and back in to heat it. Now, this is about 2.4 metres in diameter and about 6.5 high. So you can see if we're going to go to 3 metres in diameter, 7.5, 8 metres high, it's still bigger than this. So that'll be the store. And there's a nice picture here. This is the inside of the tea cozy.
The UFA, okay.
So this is the.
Right, okay. This is the inside of the
inside, because it's two skins. So the actual outside bit is going to be bigger than this.
This is the outside of the inside, yeah.
No, it's the narrower bit.
It's the inside of the.
It's the inside. This is the narrow bit. So.
This is the bit that goes on the inside, but.
Yes.
This is the inside of the inside.
Yeah,
that's the outside of the inside.
You're absolutely right. And then so the top, then it's actually bigger. It's actually wider than this to give you a feel for the scale.
Of course, with you.
We are going, as I said, a lot bigger.
Yeah.
And if we come over here, we're going to have a look. These are some early trial castings for our cheese wedges. So we want to get the casting process right. So inside each one of these, you have a steel coil, and we put electric elements directly inside each block. We're going to have 6 cheese wedges on a layer, and the store we're building will have 6 layers.
Right, 36.
36 at 1.5 tons each.
Cool.
So you're going to be up at 54 tons just for the blocks.
Yeah.
With everything else, we're probably about 60, 70 tons.
How you get delivered aluminium is interesting, isn't it? It's literally the same form as gold is transported.
Oh, it's lovely. So this is all recycled aluminium. So this is only 90% pure. We don't need any good quality grades at all. The aim is to actually go straight from the remelter to a block. That's our plan, because at the moment we don't want to deal. There are a lot of nasties with aluminium when you're recycling it, that you need scrubbers and you need a lot of equipment. It's just not worth us doing it. So we just buy. So we buy basically the remelter takes the old engine blocks, everything like this, melts it, and they form these ingots. They're very common and they're different grades. So some of them will be higher quality, better sorts of aluminium. As I said, we like the lowest grade.
You don't actually even storing
care.
heat. Yeah,
you don't care. So what we ideally want to be is located next to a remelter, where we literally take it, they only melt it once, because at the moment we melt it twice, which is inefficient. We melt it once and we make our blocks and literally go from scrap, melt, block.
Okay, cool. What's the long-term plan of melting? Is that, I suppose that's done at their end, but that will always have to be?
No, it can be electric.
Induction.
Induction furnaces are really good, and they're more efficient and they're quicker. So a lot of the time, you look surprised.
But induction hob.
No, but it's like, for aluminium is obviously electrically conductive, so induction works on it,
with it, right.
And you need to get the right frequency. So they can use electric for both steel and aluminium, but they're different frequencies. The general rule is you want some molten aluminium in there when you add your other blocks, and then it all works very well. And you tip out some of the liquid and then put some more solid in.
Right, okay.
So the actual aluminium melting process, that is a very easy one to electrify. We started off, ours sadly uses gas. It's on our roadmap.
Start somewhere.
But we didn't actually have a big enough electrical grid connection to electrify it. So we started with gas. We have electric ovens still, but the aim is the whole process should be electric. That is our
amazing.
aim.
There's a roadmap. That's the important bit.
It's the roadmap.
That's really, really cool. Amazing. Are these the elements? Are they?
No,
they're the anchoring
lifting.
points.
These are for handling. So everything. So the elements. We only got a few elements in here because that's not the bit we wanted to test.
Okay.
We're just very much about how do we get the blocks so it can pop out of the mold. So we've been doing a lot of work on the molding and the release and everything like this.
Got it.
And we're making. We're pretty much there, I think, for as far as it goes. So we start in about a month's time. We have to make a block a day.
Right, okay. And you've got that many
orders?
No,
we'll be building the unit out the back. So
right, okay.
This should be running in October, so 36 blocks.
Okay, amazing. Have you already had interest from
yes, so we are hoping, we get inquiries from all over the world. It is quite, some of them we can't manage because we're not going to be in those sort of countries for a good number of years. We're basically focused on Europe to start with, or the UK and Europe to start with. Then we've got a plan to go to the US, maybe Australia. But we do get inquiries from all over the world, and some of them we just have to go, we can talk to you, but we can't actually help you at the moment.
Yeah.
Our craziest one was our biggest one was a new alumina refinery.
Right.
So when you make aluminium, before you take the bauxite ore and you have to sort of purify it. And the purification process uses lots of steam, And they asked us to do some modeling because they were interested in using solar panels and heat storage and to do the steam, because most of the energy is just in heat in it.
Yes.
And for that, we needed 400 heat stores of the small size, or 200 if we go twice as high. So you're kind of going, okay, well, I don't think we're quite ready to there. We want to scale and everything like that. But that's the sort of the upper end. And then in the UK, it tends to be food producers, textiles, as you said, brewery. When we go to get, if there's sort of piece of interest, we had Brewers, I think we had Brewers Monthly, a lot of interest came from that. So it can be quite specific related to where information goes out. But what I want to be is in October is because we've gone up in size, I want to have this, so people say, what am I going to buy? I'd actually like to say that.
Yeah.
So at the moment, because of the intermediate size, we've slightly been, we can show you what it looks like, but it's so much easier when you've actually got a version. Then you come and say, it's working, just come and have a look at it.
See it in real life. That's amazing. Would you be able to tell us who the first brewer might be?
Probably won't be a brewer, and I can't tell you, but I am hopeful.
Yeah.
We have our first signed commercial contract by October, November. That is my current target for delivery next year.
I'm aware of a few brewers that are trying to claim that, net zero beer. Tastes similar, but
there are a number. I think. And then there's a size issue as well, which is interesting enough, which is, we have had inquiries from, smaller brewers. It's just not big enough for us now. So there's a sort of cost to deploy and everything like that. So when we look at it, often they go, we go, it doesn't make sense.
I'm on board. Cool.
Oh, let's look at the Foundry. We haven't looked at. So just to remind you. So we'll go up and have a little wander and look at the Foundry. The oven, which I don't know if you remember from last time, should have done. We
looked at it, yeah.
So we've got the big oven. You can easily walk in there. We've got your equipment. So this is running at 600, heating up your rocks. And we've got a little ashing furnace, which is at 640, which will be melting the aluminium. It's probably going up to about 800, I suspect that. This is the old furnace we used to make with aluminium. Can't hold very much aluminium in there, so this is due to be sold. And then we like to have this here because aluminium engine block.
Yeah, of course.
So that for us is lovely. That's nice.
Yeah. Yeah, it's not often you see aluminium that sort of density, is it?
No, so it's quite common, and there is a interesting issue for car manufacturers, which is when we switch to electric vehicles. So engine blocks are made from really low grade aluminium alloys. So every time you melt them and remelt them, and it's something like 80% of all aluminium or 75% of all aluminium ever made is still in existence. When you remelt them, they tend to have bits of steel and things like this. So they get different sort of contaminants from metal per se. So the alloy, there are certain alloy grades that people want, and then they tend to be taken. So you tend to take them down in sort of the quality. So casting engine blocks, you can use relatively low grades, lots of silicon. But the problem comes is we're going to hit peak car engine scrapping in 2032, but no one's going to be making new engines. So there is this concern within the industry is what do we do with the casting grades? Because often the only way to improve them is to add pure aluminium.
Right.
But if you have to add if you have had 8 tons of pure aluminium to one of this, then it's not really going to work. So there is a sort of a big question, which is how do we take some of these poorer grades and improve them without using lots of primary aluminium?
Is the quality of the aluminium why I can see? Is this what I see here, or is that just the casting process?
It's just the casting process, but it's more because they're not particularly stressed. So if you imagine body panels where you stretch the material, if you have too much iron in there, for example, it cracks. So it's not ductile enough. So you need to control the grades very carefully. But car engine blocks, relatively well understood, relatively low stress. It doesn't matter. But of course, most of the uses for aluminium, you might be looking at high quality extrusions where you want a lot of detail, and again, then you start to need very much more controlled chemical compositions. So we want, I'd say, we want all the rubbish. We want all the stuff that no one else wants. Because the only thing we want is the conductivity. So the 90% we have there is actually better than we need. But that's sort of the lowest grade.
Because the bits of steel still conduct and hold heat.
Yeah, I'd have the whole lot. I'd have everything in here could go in.
And that's helpful for the whole supply chain and everything else.
Well, I hope so, but also from a cost perspective, we just don't have to, you don't have to have the same quality controls. It's like, if there's a bit that's like, we're not quite sure what it is, give it to Caldera would be the right way. Because at the end of the day, it'll be an aluminium alloy with either too much magnesium, too much iron, too much silicon. It'll just be an alloy that nobody wants, but for us, it's fine.
Yeah, great. And it's going to a good purpose.
So, because you like equipment and big stuff,
I do.
Do you want to come have a look at the tinning furnace? So normally, we can dress you up. If you want to be dressed up, you will be wearing some of this. You don't need to wear that for what we're doing today, but you might like to have a little go. So if we come up here, you can see the spare crucible down there.
Yeah.
That's the size of the crucible inside.
The crucible.
Crucible. So
crucible. And that's where you pour the.
So if I remember rightly, I need to lift. I'm not normally allowed to do this. Something about
been off the tools for a while.
Most responsible adults. I'm not considered to have the right patient threshold.
I know that phrase.
So this is where we melt all the aluminium. So we put it in here. You've got gas comes around the outside of the. It's a graphite crucible.
Right.
So it heats up to about 1,000, 1,100, but it melts the aluminium very quickly. When you're about to do the casting, you need to throw a few chemicals in to make it pour better and just to remove
Nasty.
gases. I don't know.
Right. Okay. So this is an upwards firing. Oh, this is fired from the outside. This is
Just
like
runs
an
around the
oven,
outside, so it's like
and then exhausts out there
an
with you.
exhaust out there. So
Like a clay oven. But it's not clay, obviously.
yes, it's refractory
But it's
brick all around the outside and refractory concrete.
Okay, right.
So we can take the top off when we need to, but you shouldn't need to apart from when the crucibles do have a sort of finite life.
Yeah.
So they do need to be changed every so often.
Yeah.
So lock that in place. And then this is the fun bit, the whole thing tips.
Yes.
So this weighs about 2.5 tons, the whole thing tips up and we pour the aluminium out and it goes down this little chute, which is called a launder, and it goes into the
casting.
Yeah, exactly there.
Cool. So this whole thing, once it's molten, tips, but it's a gas-fired appliance.
Yep.
There's a gas pipe. Is that a flexible gas pipe there?
That is, yes, but I think if we go down and look, you'll see, we can have a look at the controls on the burner.
Yeah.
It's probably just like a big boiler if you're really honest.
Yeah.
So the main thing is where the connection for flue is split on this point. So as it tips over, it comes apart. Here we have the gas supply. So this is the burner.
Yep.
It's a 2-inch pipe.
Yep.
About 500 kilowatts of gas we can get through here.
Yep.
Bring this over the building. And what you see is, so gas comes in, just trying to think which side it will do. That's the burner. So if I look around
I
this
actually
side.
used to service this kind of stuff when I was doing commercial.
There you go.
There it is, comes in. You're on a flexible pipe there.
But it will also have a flexible bit here.
Yeah.
Because that's rigid and it's got to allow the whole thing to tip
It's
together.
there. It's that
flexible connection
kind of
under the cover.
Cool. Okay.
And this is the motor for driving the tipping. It's hydraulics. So that's a hydraulic pump. And so very, very simple. If we had a more advanced one, what we would want to do is have a recuperator.
Yeah.
So we preheat, we take the exhaust gas coming out, we cool it, and we preheat the incoming air.
Amazing.
Because everything's at 500 inside the store, you know, there aren't any fittings that work at 500.
Yeah.
You know, any steels tend to creep, so we weld everything.
Of course.
So, don't know if you've come across orbital welders before. A lovely bit of kit. So we're just going to show you what our orbital welder work does. This is a pipe. This is, look at the inside of that. That is an orbital welder. Look at the quality of that weld.
Yeah.
You cannot even see it on the inside or the outside.
Yeah. So for the camera's interest, we're looking at this. So there's a join in the middle here, which is like perfectly flat, and there's no resistance almost in the middle there. You can see it's the cleanest weld you could possibly get, basically.
And we make it with this fabulous little bit of kit here, which is, you basically put in your 2 bits of pipe on either side. So you can effectively...
Turned on, is it?
No, it's not turned on. So you can effectively, the tooling, but you put the pipes in, you have to get the spacing just right between them. And then there is a tungsten, well, you need gas around it, and there's a tungsten welding bit that goes the whole way around. It just does this perfect little weld.
Wow. And does it rotate the pipes as well?
Yes. No, it doesn't. The pipes are held, but the actual tungsten bit can go the full 360.
Moves around. Oh, I see. So you like press a button and it moves around.
Look. There, you can see it.
Oh, I see.
So it can rotate the whole way.
You leave in a precise, I don't know, half a millimetre or something between the two, right?
It's all set up. So you get very, very good quality welds time and time again.
Wow.
And when you're welding, as you may know, when you're welding tubes normally, trying to get your hand around and get a good weld is very difficult. It just fixes everything.
Yeah, that's really cool. Is that only a thing that's available for aluminium? Or
Steel. This is all stainless steel.
Well, I didn't know about that.
They're quite expensive.
Yeah, okay, right. Makes sense. This heat exchanger here, is this is the size of a coil per
wedge.
Per wedge.
So we fit this in. There's one of these per wedge.
Yeah.
And it's made from a single piece.
And then are those linked together series, parallel? How is
Depends. So we can do, they're normally linked, at least some of them in series, but it depends on what the customer wants, because you can change the amount of power we get out by changing whether they're in series or how many are in series and how many are in parallel.
So do you bring all of the tubes out and then you can basically...
No, we join them up inside when we make it, so you need to make a decision. but it means that
with you.
we can do a ton an hour, or we can change the configuration to do 2 tons an hour of steam. So it depends
So
on
it's about duration versus
duration versus power.
out
Yes,
with
exactly. And generally, the higher the power, not only less duration, but also you can't use as much of the store.
Yeah.
So if we're taking power out really strongly, then you can't cool it down as much because I need a bigger temperature difference to drive it.
Yes.
Whereas if you can take it out over a very long period of time, we can bring the store right down low.
Amazing. That's really cool.
So, got a little experiment for you, and we're going to do a little first that we haven't done before. So, we need to make your own little warm stone block.
Cool.
Where we'll get the molten aluminium. We're going to get hot rocks. We're going to pour it all together and let it set. But we're going to do something slightly different. We normally have, when we make a full-size block, we normally have electric elements in and the steel pipe. What we're going to do this time is we're going to put a steel pipe in as well, and then we're going to make some steam while the block is still hot.
Yes, I'm up for that.
So if you're up for that,
yes,
that's what we're going to do.
Amazing. And I get to put on this stuff.
You get to put on all of this. You get to look like a spaceman.
Amazing.
You know, scare the children. It's perfect.
Amazing.
You know,
Thank you so much. So James mentioned earlier on, I'm able to do a little experiment here. I'm joined by Michael. Hello, Michael.
Hello.
You're going to talk us through it, get me suited and booted.
Yep.
What's first?
Right, so let's get you in some PPE first.
Have you got another helmet?
Well, we have indeed. Here you go. Before you pass out.
Right, let's.
Magic. That's it.
Slight.
It's okay. There you go.
There we go. That'll be all right. Okay.
So the hot bit.
Wow. Ooh. Wow.
That's it.
Okay.
Perfect.
Oh god, this is actually quite nerve-wracking.
It's okay. There you go. You got the weight.
You wouldn't want to be on the beer on the night before.
No.
Oh yeah, I've got to re-grab this. Get a good shot of that, Harrison.
Nice.
Yeah?
Just keep pouring until it's all the way to the top.
Will there be any left over of this, or is this the...
The more you get in there, the better. There might be some, yeah. And once you've finished, you can put it back on the table to the left. Lovely. That's a good amount.
Is that good?
Yep, that's good. If you put that to the table on the left. And if you just knock the side of that tray,
Yeah.
That's it. Just keep going just a little bit more. That's it.
Slight overfill.
Perfect. That's great.
Yeah? Do I get a job?
Perfect. Yeah, you get a job.
Oh,
You're
yes.
hired.
Thank you. All right, cool. We're moving this around to our little experiment area, ready to try and make steam, which is actually what this essentially is used for, to generate steam to move heat. One stone-baked pizza coming right through. Oh, mamma mia, I can feel the heat coming from it still. Et voila. We've got a tub of water down there, which we're going to pump some water into, which will make contact with this just under 400-degree block. As soon as it makes contact, obviously that's above 100, so we should have instant steam. I'm going to stand back a little bit. Hey, there we go. Water expanding 1600 times. Okay, whilst that water's bubbling away in the background there, James, Guy, and Michael, thank you so much for inviting me and letting me get sort of hands-on with this. I think you guys will agree this is an amazing solution. We have to help with the grid peaks and troughs in demand. This is an amazing, very unique and different solution that I think obviously is part of the solution. So guys, thank you once again. If you want to see more innovation like this, make sure you subscribe to this channel, like the video, and we'll see you on the next one.